Hippocampal Health. In the following presentation, we will be examining the importance of the hippocampus in regular mental functioning by focusing on physical and dietary activities that promote hippocampal health. The target audience is regular, busy people, but the concepts discussed can be useful for the young and old as well. The hippocampus is vital for learning, memory, and spatial navigation, emotional behavior, motor behavior, and regulation of hypothalamic functions. Atrophy and damage to the hippocampus has been associated with Alzheimer's disease, where negative changes are considered a major indicator of the disease's presence and progression. Depression, where prolonged states cause volume loss in the hippocampus. Schizophrenia, where hippocampal volume loss of modest degree has been associated with the condition. Epilepsy, where post-mortem studies of patients with epilepsy found that most sufferers had hippocampal sclerosis upon death. Hypertension, which is considered a putative factor that leads to hippocampal atrophy. Cushing's disease, where studies show that if the disease is properly treated, hippocampal atrophy is reversed, and PTSD and head injuries, both associated with hippocampal atrophy. The previous suggests that aggregating information on activities that improve the health of the hippocampus will help improve the mind and body. The hippocampus is part of the limbic system, which consists of the hippocampal formation, amygdala, septal nuclei, cingulate cortex, entorhinal cortex, perennial cortex, and parahippocampal cortex. The hippocampus consists of the cornua monis, or Ca for short, including Ca1 through Ca3. The hippocampal formation consists of the dentate gyrus, hippocampal proper, and subsidicular cortex, which is a mirrored structure found in the temporal lobe of each cerebral cortex, and whose shape resembles a seahorse, hence the name. Hippocampal means seahorse in Greek. Figure 1 demonstrates their structure via the entorhinal cortex and fibrio-fornix pathways. The hippocampus influences the prefrontal orbital-frontal cortices, cingulate cortex, piriform cortex, perennial and postperennial cortices, striatum, amygdala, septum, mammillary bodies, thalamus, and hypothalamus. The hippocampal network flows mostly unidirectionally and includes the following pathway. The entorhinal cortex sends information to the dentate gyrus and Ca3 via the preforeign pathways, designated as lateral or medial depending on where they start within the entorhinal cortex. Ca3 also receives input from the dentate gyrus via mossy fibers, which are the axons of the dentate gyrus. The Ca3 then sends input into the Ca1 region via the Schaeffer's collateral pathway, or to the contralateral hippocampus, the mirrored half on the other side of the brain, via the associational commissional pathway. The Ca1 region then projects onto the subiculum, with the points furthest away creating a pathway, and the points closest together creating another. Both the Ca1 and subiculum then project back onto the entorhinal cortex, emulating the way they connect with each other, via the furthest points of the two projecting onto the lateral entorhinal cortex and the closest projecting onto the medial entorhinal cortex. Explicit memory is thought to be acquired through one or more of the following areas of the cerebral cortex: prefrontal, limbic, and parieto-occipital temporal. From here, the information is transferred to the circuit mentioned in the previous slide, specifically the parahippocampal area and perennial cortices, entorhinal cortex, dentate gyrus, hippocampus, subiculum, the back to the entorhinal, para, and perennial cortices. Damage to the right hippocampus creates issues with memories associated with spatial recognition, and to the left hippocampus, issues with memories associated with words, objects, or people. Damage to these areas hurts the formation of new memories, sparing old, demonstrating the importance of the hippocampus in responding to new novel stimuli, and implying that a healthy hippocampus is involved with long-term memory storage. New explicit memory is thought to be formed through the process of encoding, consolidation, storage, and retrieval offering a potential way to exercise the hippocampus, as intentionally memorizing and retrieving information works out the hippocampus and the associated networks. As we stated in the previous slide, damage to the hippocampus can impact spatial memory. So does physical activity also improve the health of the hippocampus? According to a study by Erickson, hippocampal volume loss can be mitigated in aging adults if they participated in regular moderate intensity exercise. Their study was based on the 1 to 2% natural volume loss per year found in older adults without dementia and demonstrated that through regular aerobic exercise, older adults could not only slow the volume loss, but moderately increase it. Their findings showed average increased volumes of 2%. What was unique about their findings was that the exercise only impacted the anterior hippocampus, which includes the dentate gyrus, subiculum, and CA1 areas, which are areas most damaged during the aging process, with the areas least impacted by aging in the hippocampus not showing any changes. The researchers also found increased serum levels of BDNF, which is associated with better memory function and increased hippocampal density. The changes they found led them to claim that the hippocampus remains plastic even into late adulthood, and that aerobic exercise has neuroprotective qualities. Additional studies demonstrate that exercise causes an increase in additional neurotropic effects, such as increases of IGF-1 and VGY and the hormone adiponectin, all of which improve the dentate gyre area of the hippocampus. Fardell also reports an increase in the rate of memory executive function when exercise is included on a regular basis. The findings of these studies all support the idea that we can literally exercise the hippocampus through exercising the body, improving both in the process. Caloric restriction and intermittent fasting were both found to positively impact the dentate gyre region of the hippocampus, as the contrast this brings to our body and the reaction it creates increases hippocampal activity. Curcuminoids and flavonoids, both subtypes of polyphenols, are shown to cause an increased BDNF and glutamatergic reaction in the hippocampus, increasing plasticity. A reduction in cognitive decline has been linked to the consumption of polyunsaturated fatty acids in elder studies, suggesting a link to the hippocampus. Phytoestrogen supplements have also been shown to improve cognitive functions that the hippocampus regulates, also suggesting a link. Specific diets have also shown improvement, such as when mice with induced Kabuki syndrome were placed on a ketogenic diet, causing a rescue of both the neurogenesis defect and hippocampal memory abnormalities in their brain. If an individual were to arm themselves with the previous information and design their life around impacting the hippocampus in a positive way through mental, physical, and dietary activation, they will see a change for the better in their personal life. This goes for the young and old and those busy in between. An example of this is seen during an experiment involving participants with type 2 diabetes were placed on a Paleolithic diet combined with 180 minutes of aerobic and resistance exercise each week in a group that just did the diet. The combination of hippocampal-focused diet and exercise and those without was significant weight loss, improved insulin sensitivity, increased oxygen uptake, increased functional brain response within the right anterior hippocampus, right inferior occipital gyrus, and increased volume of the right posterior hippocampus. Memory, though, did not show improvement, suggesting that it is a non-inherent aspect dictated solely by the health of the hippocampus, but is a process that itself must be practiced. The hippocampus is quite literally our doorway to reality, as one that is healthy functions in a way that allows us to record and retrieve new information and maintain our orientation with the world around us, and one that is unhealthy, such as seen in those suffering from Alzheimer's disease, robs us of our ability to comprehend and function. Focus should be placed on living a lifestyle that promotes hippocampal health throughout the human lifespan, and not simply focus upon when we are older and facing cognitive decline. And that is my presentation. Thank you for listening.